All right, so today is our final transformation, okay? Again, to review, we've done translations, reflections, and rotations so far. We've taken a quiz over it. Most of you guys have shown that you, for the most part, understand those old school transformations. Those are transformations that you have seen before. Now, you've never had to work with rotations quite as much as this year, but you've at least seen them before. Dilations is what we're talking about today. All right, and dilations are super easy. Okay, a dilation is when we make a figure bigger or smaller. Okay. All right. So, did I say we were going to change the shape?
No.
Are we going to change the orientation? No. We're changing one thing, the size, and that's it. Okay? We're going to change the size. Now, going in, you need to understand the term scale factor. Okay? A scale factor is the number we multiply by in order to make it bigger or smaller. Okay? We'll use scale factor. We'll take our coordinates and we'll multiply them, all right, by the scale factor to make our shape bigger and smaller. So, if, and here's a couple things to remember as well, okay, with scale factor. In our scale factor, if our scale factor is greater than 1, greater than 1 means it's going to get bigger. Less than 1, which is a fraction or a decimal, it's going to get smaller. Okay? Simple enough. Okay? Greater than 1, it's going to get bigger. Less than 1, it's going to be smaller. If your scale factor was 1, it'd stay the same, right?
Yeah.
So it kind of stands to reason. If 1 keeps it the same, anything more than 1 is bigger, anything less than 1 is smaller. All right. From there, we need to understand certain keywords. Okay, if they say that we cut all dimensions in half, then what would our scale factor be? If we cut all the dimensions in half. In half.
Less than 1?
Cut all the dimensions in half.
It'd be half.
Which is?
0.5.
0.5. All right, 0.5 is half. Or you could do 1/2. Either way is fine. All right, but we got to hear that. Okay, if you're cutting it into a third, that would be 1/3. If we're doubling the size, what's the scale factor?
Times 2.
It would be 2. Okay. If we're going to do, I don't know, triple the size, it's 3, so on. All right. We need to be able to see those words and identify what our scale factor would be. Okay. Now, let me show you an example of dilation. All right, let's say we have, we'll go with triangle A, B, C again. A, B, and C. It's an ugly B, but you get it. All right, now we are going to double the dimensions here. Okay, double. Which means our scale factor will be what?
Times 2.
It'll be 2. Scale factor is 2. All right. So, what we would do here is we would take every point, all right, A, B, and C, all right, and let's look at their coordinates. A is at 1, 3. B is at 1, 1. And C is at 2, 1. Does everybody see how I got those coordinates? So for scale factor, we're going to multiply by everything by the scale factor and get our new coordinates. Okay, so A prime would be what? What was it? 2 and 6. B prime would be 2 and 2. C prime would be 4 and 1. All we did was multiply every number by the scale factor. Okay, so let's graph those. All right, for A, we go 2, 2, 4, and 6. That's right here. There's my A prime. B is 2 and 2. There's B prime. And then C was 4 and 1. There's C prime. So there we go. There's our new triangle. That's simple enough, right? It's double the size. All right, now, here's a fun way to check yourself. Okay? We want to check ourselves. We just did a dilation, okay? And we used the origin for the center of our dilation. And I can tell you, I'm not going to ask you to use anything else but the center of dilation as the origin. Okay? So, if I go from A, here's my A, and I go make a straight line through the other A, the corresponding A, where does that line take me to? The origin. So does that one. So does that one.
Cool.
Okay? So if you do this correctly, then that resulting line should always take you through the origin. Does that make sense? It's a quick way of checking your answer. And obviously you don't have to draw that line. If this was Star Test, you could use the edge of your paper and just kind of fold the edge of your paper over to make sure that if you drew a line, it would go through the origin like it's supposed to. All right, a couple other things I want to point out. What was the side length of AB on our pre-image? 2. What's the side length of AB prime? AB prime, 4. Okay, so our side length doubled when our scale factor was 2. All right, now. So, line AB was 2. A prime, B prime was 4. All right, so we can see that our side length doubled there. What they're going to try to trick you with, all right, in the STAR test is with area. Okay, the area of ABC, triangle ABC. We do base times height divided by 2. That'd be 1 times 2 divided by 2, which is 1 times 2 divided by 2. 1. I can't really make math problems much easier than that. All right. All right. Area of triangle A prime, B prime, and C prime. What do you think it's going to be? Since we're doubling the dimensions. So what do you think it's going to be?
8.
A lot of people say 2.
2.
A lot of people think it's 2. Well, let's look. Base times height, 2 times 4, which is 8, divided by 2 is 4, not 2. Okay? So, when the dimensions of our shape double, the area does not double with it. Okay? The area actually goes up at a different rate, so we need to make sure that we check that. Okay? Any questions there? All right. Let's say we'll do another example here. All right, let's start out with I don't want to do that. All right. I want to use a scale factor. I want to cut these dimensions in half. Cut the dimensions in half. Okay, so what would my scale factor be?
Wait, how do you figure out the scale factor?
If I'm cutting the dimensions in half,
Oh, 1/2.
it'd be 1/2. All right, so let's say this is A, B, C, and D. Is this going to get bigger or smaller?
Smaller.
Smaller.
Good. All right, so got to write down all the coordinates. We got A, which is negative 2 and 2. B, which is 3 and 3. C, which is negative 3 and negative 3. And D, which is 5 and negative 1. So now for our new shape, I just got to cut all these in half. So this would be negative 1 and 1. Does anybody not see how I did that? Just divided them both by 2. This would be 1.5 and 1.5. This would be negative 1.5 and negative 1.5. This would be 2.5 and negative 0.5. All right, so negative 1 and 1, there's my new A. 1.5, 1.5. There's my new B. Negative 1.5, negative 1.5. There's my new C. 2.5 and down a half. There's my new D. All right, so there we go. All right, you can see that it got half the size. Okay, and we can. Again, we can check our answer really quickly. You can see that it all leads back to the origin, right? All right. So, the last thing in this lesson, and again, this is not a very long lesson. I don't feel like this is one of our harder transformations. You do have to look at the coordinates a little bit more than you usually do. But I don't feel like it's too out there. Now, if we're going to do this with algebra, this is actually the easiest algebra representation there is. Okay? If we're going to use algebra to solve this, basically what we're going to do, we're going to say x and y. All right? And then as far as what you want to, you're going to always multiply your x and your y by something, right? So what we'll do is we'll put a just a placeholder to represent all numbers. Okay, so we'll just say, for now, we'll say ax and ay. Okay, where a represents the scale factor. Okay, so if we had 5 and 7, the scale factor was 3. It would be 3 times 5 and 3 times 7, which would give us 15 and 21. It's super simple, right? Okay, if we had 12 and 21 and our scale factor was 1/3, then we would do 1/3 times 12 and 1/3 times 21, which would give us 4 and 7. Okay, the reason I think that this is the easiest as far as algebraic representation is because you have to do this process anyway whenever we're working with the graphs. Okay. All right, and that is our lesson over dilations.